So we're continuing looking at examples of spinors in physics. In the last video, we introduced Jones vectors for representing the polarizations of electromagnetic waves. The top component gives the magnitude and phase of a horizontally polarized wave, and the bottom component gives the magnitude and phase of a vertically polarized wave. By combining these two polarizations in different amounts and phases, we can get other polarizations, like diagonal, anti-diagonal, left circular, and right circular polarizations. In this video, we're going to find that we can rotate between all these polarizations by using special matrices called SU2 matrices. And this will reveal how there's an angle doubling relationship between physical space and wave polarizations. This will show us that Jones vectors are actually spinors. So when it comes to light waves in real life, we can manipulate the polarization of light waves using various optical devices, like polarizers and waveplates. In the world of math, these correspond to multiplying our Jones vectors by various matrices called Jones matrices. I'm not going to discuss polarizers in this video. Minute Physics and 3Blue 1 Brown have already done really good videos on polarizers that I've linked in the description. For this video, the more relevant optical device I'm going to talk about is the waveplate. A waveplate is a device that essentially rotates one polarization into another by introducing phase delays. You probably already know that a light wave will change speed when it passes from one medium to another, such as passing from air into a crystal. Because of the change in speed, by the time the light exits the crystal, there is a phase change in the resulting wave, compared to light that did not pass through the crystal. In special crystals called birefringent crystals, the phase change is actually different in the horizontal and vertical directions. This means that a light wave whose horizontal and vertical polarizations are aligned before entering the crystal can have a phase difference by the time they exit the crystal. For example, let's say we take a birefringent crystal and aim a diagonally polarized wave D towards it, where the horizontal and vertical components are in phase. If the crystal introduces a quarter cycle phase change in the vertical component, then the resulting wave is a left circularly polarized wave L. This crystal that changes the vertical polarization by a quarter cycle is called a quarter wave plate, and it is represented by this matrix here. If we apply this matrix to our diagonally polarized Jones vector, it leaves the horizontal polarization alone, but applies a quarter phase change to the vertical polarization. Remember, the imaginary eye is a quarter turn around the complex unit circle, so it represents a phase change of a quarter cycle. If we apply this quarter wave plate again, by multiplying by the same matrix, it will cause the H and V polarizations to realign again, but with an opposite sign in the V polarization, which is the same thing as a half-cycle phase change. This gives the anti-diagonal polarization A. Applying the quarter wave plate again, the V polarization is changed yet again to give negative I, which is a 3/4 cycle phase change, which gives a right circularly polarized wave R. And applying the quarter wave plate again brings us back to where we originally started with the diagonal polarization D. So this matrix here allows us to rotate around in a circle between these four polarizations, D, L, A, and R. And actually, if we replace this imaginary I, which represents a quarter phase, with an arbitrary phase, we can rotate continuously around this circle with any phase we like. And this gives us all sorts of different polarizations, including elliptical polarizations. If we rotate around this circle, the polarizations look like this. Now, it's interesting to note that if we put a horizontally polarized wave H through this quarter wave plate, nothing actually happens. The output wave is still horizontally polarized. But that doesn't mean that this waveplate is totally useless for horizontally polarized waves. We can make something interesting happen if we rotate this waveplate by 45 degrees. In this case, the output wave is a left circularly polarized wave, L. This isn't surprising if you think about it, because the setup we have here is the exact same setup as our previous example, but with everything rotated in space by 45 degrees. The physics is the same, we're just viewing it from a different angle. However, when viewed from this angle, our quarter waveplate rotated by 45 degrees is represented by this new matrix. You'll notice that this matrix contains a phase factor, e to the I pi over 4, written in gray. We'll see later that we can actually ignore this phase factor, but for now I'm going to include it. You can think of this new matrix as a combination of three matrices. The first matrix will rotate our coordinates 45 degrees, so that our coordinate system is now aligned with the main directions of the waveplate. Then we apply the original quarter waveplate matrix we saw in our previous example. Then we rotate our coordinate system back by 45 degrees in the opposite direction. When we combine these three procedures through matrix multiplication, we get this new matrix, which represents a quarter waveplate angled at 45 degrees. As you can see, it turns a horizontally polarized wave into a left circularly polarized wave. Once again, I'm ignoring this phase factor outside here, and I'll explain why in a moment. If we apply this waveplate multiple times, we get waves that are vertically polarized, right circularly polarized, and then we return to horizontally polarized again. So this waveplate rotated by 45 degrees, represented by this matrix, takes us in a circle around the polarizations H, L, V, and R. And again, we can actually rotate continuously along this circle to get all sorts of polarizations in between. We just need to take our rotation matrices from before and set them to an arbitrary angle theta, instead of using 45 degrees. This corresponds to rotating our waveplate by an arbitrary angle. Now, let's get back to all these phase factors that I've been ignoring. Why is it okay to ignore these phase factors? Well, we know that if we take a diagonally polarized wave and shift the vertical component of the wave by a quarter phase, we end up with a left circularly polarized wave. But now instead, let's shift both the horizontal and vertical components by a quarter phase. The result is just shifting the entire wave by a quarter phase. The wave's diagonal polarization is unchanged. We've just shifted the wave along the axis of travel. So when it comes to using Jones vectors to represent wave polarizations, multiplying both components of the Jones vector by the same phase has no effect on the wave's polarization. All this does is shift the wave along the axis of travel. So when it comes to polarizations, there are multiple Jones vectors that represent the same polarization, each with a different total phase factor in front. So we can ignore these total phases when studying wave polarizations, because total phase shifts don't change the polarization of a wave. So we have this matrix for rotating in a circle between the polarizations D, L, A, and R. And this matrix rotates us in a circle between the polarizations H, L, V, and R. Putting these two circles together, we get a sort of sphere shape. This indicates that there should be another matrix for rotating between H, A, V, and D, and that ends up being true. Rotating between H, A, V, and D is the same thing as looking at the xy plane and rotating the wave clockwise, which is given by this matrix here for quarter turns and given by this matrix here for rotating continuously. So altogether, we see that we can arrange all our polarizations of light on a sphere like this. This is called the Poincaré Sphere. We initially discovered these three matrices for performing quarter turns on the sphere. And these matrices can be generalized to continuous angles, which allows us to reach any point on the sphere, giving any arbitrary Jones vector of amplitude 1. So what's so special about these matrices? What do they have in common? It turns out that these matrices all belong to a group of matrices called U2, the unitary group of 2x2 matrices. But what does this mean? Well, the key idea for rotating across this sphere is that we are not changing the amplitudes of our waves. So we're just rotating the Jones vectors on the sphere without changing their lengths. So U2 matrices represent rotations on the sphere of polarizations. To understand this, let's go back to 3D vectors for a moment. One way to get the squared length of a vector v is to treat v as a column and write the squared length as v transpose v, where the transpose operation just means we flip columns into rows. When we perform this array multiplication, we get x squared plus y squared plus z squared, which is the standard Pythagoras formula for the squared length of a 3D vector. Now, what if we wanted to apply a matrix R to this vector to rotate the vector? How do we determine what this matrix R would look like? Well, a key fact about rotating vectors is that their length doesn't change under rotation. So if we take our formula for the squared length of v and then apply our rotation matrix R to v, this should not change the result of the original squared length formula. So these two formulas must be equal. It's a standard rule from linear algebra that the transpose of a product of arrays is equal to the transposes of the individual arrays multiplied in the reverse order. So we can write RV all transposed as V transpose R transpose. So this equation is telling us that if R is a rotation matrix that doesn't change the length of vectors, then R transpose R must be equal to the identity matrix. Another way of saying this is that R transpose is the inverse of R. If R is a 3x3 matrix with the columns highlighted like this, then R transpose involves flipping the columns into rows to give us this. Now remember, R transpose multiplied by R gives us the identity matrix. This gives us some interesting relationships between the columns of R. Notice that when we multiply any column by its transpose, we get 1. This tells us that the columns of R, if treated as vectors, each have magnitude 1. Also, if we multiply any column by a different column's transpose, we get 0. This tells us that the columns of R, if treated as vectors, are all orthogonal to each other. Matrices that satisfy these properties are called orthogonal matrices, and we write the group of all orthogonal 3x3 matrices as O3. So we know our rotations in 3D are done by O3 matrices, but we've actually missed an important detail. It's true that rotations don't change the length of a vector, but reflections also don't change the length of a vector. So this O3 group of matrices that don't change vector lengths contains both rotation matrices and reflection matrices. If we take the formula R transpose R equals the identity and take the determinant of both sides, we know from linear algebra that the determinant of a product equals the product of the determinants. And also, taking the transpose of a matrix doesn't affect the determinant, so we ignore the transpose. Since the determinant of the identity matrix is 1, this tells us that the determinant of R is either +1 or -1. Remember, the determinant of a matrix tells us how much it changes the areas of squares in 2 dimensions, or the volumes of cubes in 3 dimensions. Rotations have a determinant of +1 since rotations don't change areas or volumes. Reflections don't change the size of volumes, but reflections reverse directions, and this results in a determinant of -1. So if we only want to look at matrices that do rotations and not reflections, we have to only look at the orthogonal matrices with determinant +1. This is called the special orthogonal group SO3, where the word special means we're restricting ourselves to matrices with a determinant of +1. So we know that the special orthogonal 3x3 matrices will perform rotations on 3D vectors without changing their length. Now, getting back to our sphere of polarizations, we want to know what kind of matrices will rotate our Jones vectors around without changing their amplitudes. This sounds similar to rotating 3D vectors, but there's one key difference. Jones vectors have complex number entries instead of real number entries. If we have the complex number c equals 3 plus 4i, we don't get its squared magnitude by doing c times c, as this gives us another complex number, and magnitudes must be real. Instead, the squared magnitude is given by c times the complex conjugate of c, which is denoted with this star, and flips the sign of the imaginary part. This results in the correct magnitude of c, which is the real number 5. So when we want the squared magnitude of a complex Jones vector j, it's not enough to write j transpose j, as this might give us a complex number result. Instead, we write j transpose complex conjugate times j to get the correct squared magnitude. This combination of transpose and complex conjugate is called the Hermitian conjugate, and is usually written with a single dagger symbol. So to get the squared magnitude of a Jones vector, we use j dagger j. As an exercise, you can check that each of these Jones vectors indeed has a magnitude of 1. So if we rotate a Jones vector j around with a matrix U, the result of the magnitude formula should stay the same, so these two formulas are equal. Rewriting uj all daggered as j dagger u dagger, we see that our rotation matrix U must obey u dagger u equals the identity. In other words, U inverse equals its complex conjugate transpose. We call matrices with this property unitary. They are sort of like the complex number equivalent of orthogonal matrices, since they rotate complex vectors around without changing their magnitude. The group of 2x2 unitary matrices is called U2. And another good exercise to try is to pause the video and confirm you can get the inverse of all of these matrices by taking their complex transpose. Taking the determinant of this formula for U2 matrices, we get that the squared magnitude of the determinant must be 1. But since the determinant of U is a complex number, the answer isn't just plus or minus 1. Instead, the answer can be any complex number on the unit circle with magnitude 1. And this can be written in the form of e to the I times theta. We can check its magnitude is 1 by multiplying it by its complex conjugate and canceling the exponents. So we know that U2 matrices can rotate our Jones vectors on the Poincaré sphere. But once again, there's something we've missed. Recall that any two Jones vectors that are the same, but with a different phase factor in front, represent the same polarization. For example, each of these Jones vectors represents a left circularly polarized wave. This means that if we want to turn a diagonally polarized wave into a left circularly polarized wave, there are multiple U2 matrices that can do this, all identical but with a different phase factor in front, because we can ignore the phase factor in the final result anyway. So the group of U2 matrices has some redundancy, given by this phase factor out in front. However, it's possible to pick out a unique U2 matrix that takes us between a specific initial and a specific final polarization. All we need to do is to find the specific U2 matrix that has a determinant of +1. So if we have some U2 matrix with a determinant that's equal to a complex number e to the I theta, we can convert it into an equivalent matrix with a determinant of +1 by following the below procedure. We just multiply all the elements of the matrix by e to the negative I theta over 2. After taking the determinant, combining the exponents, and factoring, these exponentials cancel and we get a determinant of +1. This multiplicative phase factor doesn't affect the polarization of our Jones vectors, since we can ignore overall phase factors anyway. The set of 2x2 unitary matrices with a determinant equal to +1 is called SU2, the special unitary group of 2x2 matrices. This is the set of matrices that rotate our Jones vectors around on this sphere of polarizations. Again, the word special means the matrices that have a determinant of +1. We'll finish this video by explaining why these Jones vectors are considered spinors. Notice that in physical space, vertical and horizontal polarizations are angled 90 degrees apart. But on the sphere of polarizations we've created, the H and V polarizations are on opposite sides, 180 degrees apart. So a quarter turn in physical space corresponds to a half turn in polarization space. If we do another quarter turn in physical space, we end up at the negative vertical polarization, where the negative sign indicates the wave has an extra phase of half a cycle compared to the starting wave. But in polarization space, we've done another half turn and completed a full loop, and are back to where we started. When it comes to polarizations, there is no difference between a vertical polarization with a positive sign in front and a vertical polarization with a negative sign in front. The overall phase shift doesn't matter, and both are considered vertical polarizations. Since wave polarizations are unchanged by an overall phase shift, the Jones vectors in our polarization space are unable to see the negative sign in front of the wave. All it sees is a vertically polarized wave. To get back to the original wave, we do another half turn in physical space, which corresponds to another full turn in the polarization space. So a full turn in physical space requires 2 full turns in polarization space. This is why Jones vectors are considered spinors. Rotating a wave back to its original state requires 2 full rotations of the Jones vector in polarization space. So when we rotate by an angle theta in polarization space, this corresponds to a rotation by an angle of theta over 2 in physical space. For this reason, you will often see the SU2 matrices that are used to rotate Jones vectors written with half angles like this, because when we want to rotate by an angle of pi in polarization space, this corresponds to rotating our Jones vector components by an angle of pi over 2. This is how we get from the V polarization to the H polarization. In the next video, we're going to learn about quantum spin states and how they are also described by spinors that transform with SU2 matrices. Even though this is a different physical phenomenon, we'll find that the mathematics of analyzing quantum spin states is almost the exact same as the math required for analyzing polarizations of light waves. This will show us that spinors are indeed useful tools that can solve multiple problems. If you're interested in doing one last exercise, you can try rotating this Jones vector around this path, using these matrices, and checking if the final result makes sense.